Hi, folks. Doing measurements in science is serious business. A scientist must be vigilant and extremely skeptical of every piece of equipment and laboratory apparatus they have, especially if these pieces are being used to give you a quantity that is supposed to be accurate and free of any systematic error. Furthermore, we must know and verify the precision of the instruments, so we always know the significant figures of the numbers we produce in the lab. In this lab, we want to use one of the most precise instruments we have, the analytical balance, along with some statistical analysis and stoichiometry to do two important measurements. One, calibrate a 20 millimeter pipette, and two, measure the degree of dehydration of our old friend copper 2 sulfate pentahydrate. Well, you probably have heard the adage, time is money, or you get what you paid for. Well, in science, the more precise the measurements, the more money the machine will cost. Also, precision costs us in time and effort. High accuracy and precision measurements almost always requires more precautions in sample preparation and definitely an upgrade in laboratory skill. So in this lab, we're going to use one of the most precise measurement devices we have, the analytical balance. A scientist who does not learn how to use this piece of apparatus properly is pretty much doomed to introduce error into a process of which they'll not be able to recover or fix. Now, using a top-load balance, we saw that just has like a 0.01 gram precision is easy to use. Just tare it and go. Now, the analytical balance is capable of measuring mass with 100 times more precision. And as would be expected, the cost of this instrument runs about 100 times more than a top-load balance. Now we can weigh the very oils that get deposited by our fingerprints on a piece of glassware. This means how we handle our samples must be regimented. Atmospheric conditions, drafts and air movement, temperature and the proper table and leveling of the instrument all come into play at this precision. That's why there are doors even around the balance to isolate some of these factors. Now some basic rules are: keep the balance in the balance pan absolutely clean. Do not place anything directly on the balance pan. Even use weighing paper before you place the glassware on the pan. And chemicals and moist, wet objects will compromise the pan and completely wreck your results. Make sure everything you weigh is at room temperature. Warm or cool objects set up convection currents in the air around the pan and will cause drift or steady changes to the measurement. Don't lean on the table or move the balance. And as would be expected, always wipe down objects such as glassware with chem wipes to get rid of the oils on them, and then handle with chem wipes to keep your fingerprints off the objects. Static charge can also affect the readings. Handle objects with the chem wipes again, and that will help prevent some of the buildup of the static charge. Be careful to not mark or put labels on the glassware that you're weighing with this balance. The glues and markers that are used will probably change weight with the humidity or handling of the glassware as time goes on. The doors around the balance must be completely closed before you tare the instrument or before making a final reading. And be very aware of the total mass limits of your model of analytical balance. And don't put something on it like large beakers or glassware. As would be expected, mass limits are extremely important for analytical balances. Typically, you don't want to weigh anything more than about 140 to 200 grams on the balances in our labs. Yeah, you see what I mean, right? Precise measurements require a lot from us. It's the only way to eliminate the systematic error into these kinds of measurements using these kinds of instruments. A very simple test of our experimental technique in using the analytical balance is to obtain a 100 ml beaker and a small glass test tube. Well, what we do is first weigh the 100 ml beaker on the analytical balance, being sure to handle it properly with chem wipes, and then write that mass down. And then next, we weigh the small test tube by itself, handling it correctly and writing the mass down. And then we place the test tube in the beaker and weigh the two together. Now, if you've been very careful in handling and weighing, the masses of the beaker and test tube weighed separately, when added together, should be within 0.0003 grams of the mass when both pieces of glassware were weighed together. Now, repeat this experiment until you feel comfortable with your technique and you can hit that 0.3 milligram range of precision. Now that we've mastered measuring masses on an analytical balance, let's use this instrument to calibrate a 20 ml pipette. Now we want to measure the average and precision of a liquid that we deliver with the standard 20 ml pipette. Now we would expect to measure 20 mils with this pipette as per the manufacturer's specifications, right? But how good is the pipette that we've been given? How close does it meet the manufacturer's specification when considering the precision and the tolerance of this pipette? And one huge factor we must consider is how good is our individual technique when we actually use this pipette. Now, the lab instructor will show you the proper technique in using a pipette. Now, you'll be doing this kind of measurement many times in the course, so diligence and practice pays off. Now, one of the biggest steps is to make sure and first rinse the pipette with the solution you want to measure and discard this rinsing solution. You never know where the pipette's been. Now, what we're going to concentrate on is the actual calibration of the pipette using the analytical balance. Wait, the pipette measures volume, yet we're going to use a mass measurement to do the calibration? Well, yes, because we know that density is the great mass volume connector. Now we need to choose the liquid and, almost as importantly, know what the temperature is of that liquid. Then it's a simple matter of finding the density of the liquid at that temperature. Now water will be our liquid and we'll measure its temperature. From that, we can use the following table to get the density or the water in grams per mil to quite a few sig figs. The general idea is we deliver what we think is 20.00 mils of water using our pipette to a flask. We weigh the mass of the water we delivered with our superior precision instrument, the analytical balance, and compute the real volume we delivered utilizing our density from the table. The last piece we need to do this experiment is to realize we not only want accuracy here, but also precision. Now, the only way to get at the precision of our pipette is to do the same measurement several times. And in doing so, we can compute the average of our measurements, which represents our accuracy, and the standard deviation, which should represent our range or precision. So let's say we do the measurement 4 times. We can use the following equations to compute the average and standard deviation of the measurements. Now, these values do have units. And notice the n value in the equations. The n is the number of trials or samples that we ran in the calibration of this pipette. Now, the greater n is, or the more trials we conduct, the better our average and especially the standard deviation will be at representing the truth of the accuracy and the random error in our measurements. Theoretically, we can only know the truth by infinite number of trials, which of course is unobtainable. Now, the standard deviation tries to adjust a bit for this problem by dividing by n minus 1 rather than n. And one other thing to remember here is that the standard deviation is telling us where we are guessing in our value. Thus, a standard deviation should only be one significant figure, or 2 with the second value a subscript if you're interested in how things are rounded. Now, once you have the standard deviation, you can round off the average to the correct number of significant figures, since you now know which digit is statistically the one that's being guessed. We also find it valuable to compute the relative standard deviation, which gives us information about how the size of the error compares to the value or magnitude of the measurement. This is a ratio where we simply divide the standard deviation by the average. We typically report this with 1 or 2 significant figures, and since it's a ratio, the value will have no units. Now, we can report this value either as a fraction as computed, or by a percentage if we multiply by 100, or by a parts per thousand or PPT, which amounts to multiplying the fraction by 1,000. In this experiment, we'll record the relative error in PPT, parts per thousand. And one important thing we need to realize, the precision is not only determined by the pipette, but also by our ability and the technique in using that pipette to dispense volumes consistently, and our ability to measure the mass using the analytical balance correctly. The calibration experiment runs as follows. We obtain pure water that's been out in the atmosphere and has a stable temperature. We measure that temperature of the water and find the density using our table or the table that's posted in the lab. And then we obtain a 125 milliliter flask and dry the outside. We don't have to have the inside of it dry. We also need a stopper, and we'll clean and dry it. We place the stopper on the flask and weigh them using the proper handling techniques on the analytical balance. Be sure to write the value down using all 4 decimal places. With your previously rinsed pipette, deliver 20 mils of your water to the small 125 ml flask. Stopper the flask and reweigh it with this additional water. And write that value down. We'll call this mass 1. Now deliver an additional 20 mils of water to the flask. Stopper it, weigh and record your mass. This is mass 2. Do this procedure 2 more times, getting a value for mass 3 and mass 4 for a total of about 80 mils of water delivered to the flask. Now, with these data, we can calculate the mass of water delivered each time we used the pipette. For our first trial, we simply subtract the weight of the near-empty flask and stopper from mass 1. This is the mass of water delivered in grams for trial 1. For trial 2, we simply subtract mass 2 by mass 1, and so on for trial 3 and trial 4. We should have 4 decimal places on each of these numbers. Now, use the density of the water to convert the mass of water to volume of water for each trial. Because our mass values have 6 significant figures and our density probably has 6 significant figures, our volumes at this point should also have 6 significant figures. Calculate the average and the standard deviation of the volumes of the 4 trials. Remember to report the value of the standard deviation to 1 significant figure and then to round off the average appropriately based on this standard deviation. Also use the standard deviation and average to compute the random standard deviation and report this value as parts per thousand and with 1 significant figure. At this point, we can analyze our calibrated pipette to the manufacturer's specifications of this pipette. The pipette you were given is a Class A piece of glassware, which should measure 20.00 mils and have a tolerance or range of plus or minus 0.03 mils. First, what is the error in our delivery of 20 mils? This would simply be our average volume minus the manufacturer's 20.00 mils. This can be a positive or a negative number, so remember to have the correct sign. Second, does our standard deviation reflect the same tolerance of the manufacturer of a plus or minus 0.03 mils? Are we higher or lower than that value? How much of that do you surmise is because of the systematic or user error of that pipette? Third, is the results we are obtaining in our measurement the same as the manufacturer? This question is actually more nuanced than you might think. One easy way to answer the question is to first consider the full range of our measurement about the average. Let's say our average is 19.96 mils plus or minus 0.05 mils. Then the full range of our measurement would be 20.01 mils to 19.91 mils. We would hope, minus systematic error, that truth lies somewhere inside the range. The manufacturer's range we can assume to be 20.03 to 19.97 mils. If both ranges overlap, such as they do in this example, then we would say that both are the same, and the answer to our question would be yes. If there is no overlap of the two ranges, we would say no. Be sure to report this full analysis in your lab report. Finally, let's turn our new skill of measuring mass on a chemical problem. The dehydration of a hydrated salt, copper 2 sulfate pentahydrate. The idea is to grind the salt into a fine powder, weigh it on the analytical balance, place it in an oven for about 12 to 24 hours, place it in a desiccator to keep it dry, reweigh it in a week, and calculate how many moles of the water were driven out of the solid. Now, the chemical equation showing this dehydration process is shown, where M is the moles of water released by the salt. The value of M should be an integer. Now, first, we weigh out between 1 to 1.5 grams of the copper salt using the top load balance. We don't have to record the mass, not yet. Place the salt in a dry mortar and pestle and grind the salt into a very fine powder. This basically increases the amount of surface area of the solid with the dry, hot air and speeds up the reaction, which in this case is the dehydration of the solid. Now be sure to write down your observations describing the color of the salt, or even better, take a picture of the salt with a smartphone. Now, obtain a very dry 100 ml beaker, dry inside and out, and weigh on the analytical balance. Be sure to record that mass. Pour the grinded copper salt into the pre-weighed 100 ml beaker. You don't have to get every speck of the salt out of the mortar, just most of it. Now, obtain the mass of the beaker and salt using the analytical balance and record the mass to 4 decimal places. Obtain a piece of aluminum foil that can cover the beaker. Write your name on the foil so you can be identified. Now place the foil loosely on top of the beaker so that air can easily move in and out. Now if you cover the top too well, the water from the salt won't be able to escape, and you don't want that. Now place the beaker with foil on top in an oven. This oven will be preheated to about 120 to 140 degrees Celsius. Now the next day we'll remove the beakers and place them in a desiccator, which will allow the beaker to cool while still maintaining a dry atmosphere so that the water we drove off in the oven does not come back on and rehydrate the salt. Now next week when you return, we'll take the beaker, remove the foil, and reweigh the beaker and dehydrated copper salt on the analytical balance, and then record that mass. Also, write down your observation of what the salt now looks like, or take a new picture to compare to the picture of the salt beforehand. From the difference of the beaker and the beaker plus hydrated salt, we can obtain the mass of the salt and the millimoles of the salt using the molecular weight of the hydrated salt. A millimole is simply the moles divided by 1,000. This value should be about 5 significant figures based on the mass. The difference of the mass of the beaker plus hydrated salt minus the mass of the beaker plus a dehydrated salt should be the mass of the water driven off the salt. From this value and the molecular weight of water, we can then calculate the millimoles of water driven off the salt. The mole ratio of millimoles of water to millimoles of the original copper 2 sulfate pentahydrate is the M value of our equation. Now also include some observations in your report. What differences did you see in the color of the salt before and after dehydration? And how close was the M value to actually being an integer? Well, that does it for this lab. Be sure to do the pre-lab and turn it in the very first day. Catch you later.